Hello and welcome back. Today I'm going to give you a brief introduction to electron dot structures. And I had to ask myself, what's the best way of teaching this? Because this can get complicated. So I'm going to go back and do this little brief worksheet. Some of this is review about valence electrons and Bohr models, but I think it's really going to be handy because it's going to give us a better idea of what we're doing when we look at electron dot structures. Next lesson we'll actually get into building electron dot structures. But this lesson is kind of review. So what do we have here? We have element 3 through 10. These are in the second period of the periodic table. Now if I look at these, we need to keep in mind that these do not have any d orbitals yet. So that makes things a little bit easier. Okay, so let's go ahead and look at the worksheet, because of course chemistry teachers love worksheets, because really chemistry is a lot about practice. You have to practice chemistry. Oftentimes in class I'll see students do a few little examples and they'll say, I understand it, I'm good. Well, they understand it until they don't, if you know what I mean. You need a lot of practice. So that's the first key to being good at chemistry. And that includes myself, by the way. Okay, so we need to do a shorthand electron configuration of these elements. What does that mean? Well, let's go back and do an electron configuration of lithium. Now remember, up here, there's one energy level. So you would have 1s1. That would be for hydrogen, or 1s2 for helium. In essence, what you're saying is there's one energy level. There's really just this one subshell, and you can have two orbitals. I'm sorry, one orbital which will hold two electrons. Okay, so if we move down here, we have lithium, which really is 1s2, and now we're in the second energy level, and 2s1. That's the electron configuration for lithium. And yet again, it's just telling us we have two energy levels. Each energy level has this subshell, and this subshell has one orbital which can hold two electrons. So how do I write this in shorthand though? Well, shorthand means I write the previous noble gas, which would be helium. And helium is 1s2, so then I don't have to write 1s2. I just write helium, then 2s1. Let's see if I can fit that in here. Helium and 2s1. Okay, well that seemed easy enough. Now I have to go on to beryllium. Well, I just add one more electron for beryllium because I'm going over to the right. I'm just adding electrons, so I can easily put helium 2s2. Now I'm going to go to the p subshell. If I look at the periodic table, I'm in period 2, so there's no D's. I'm just going straight to the P subshells. Remember, this is the D block down here. So this would be 1 and 2 and 3 and 4 and 5 and 6. So let's look at boron. Well, boron, if I wrote out the whole thing, it would be 1s2, 2s2, 2p1. But I'm doing the notation here, so yet again I don't have to write that. I would write out helium 2s2, 2p1. So I'm going to try to fit that in here. Don't you wish chemistry teachers would make these spaces bigger? And I have only myself to blame. 2s2, 2p1. Now let's just keep adding helium 2s2, 2p2. Nitrogen. So let's write helium 2s2, 2p3. This is sort of like when you zen out and just sort of concentrate. 2s2, 2p4, helium, 2s2, 2p5. Now let's think about this for a brief second. First of all, these only have 2 energy levels. The second thing is valence electrons are sort of defined as the electrons in the outer energy level, and you would combine the S and P subshells together. The D's get a little bit tricky, and that's why we skipped over the transition metals and we're not talking about them right now. So in essence, what we're saying here is there's 2 electrons here, there's 5 here, so there's 7 electrons in the outer energy level of fluorine. There's 6 here. Right here we have 5, 4, 3, 2, 1. Of course, neon has a full octet, so actually if I wrote neon, I would just write neon. It's like, yeah, I'm neon. I don't even need to write anything, but I could write out the whole thing here. I could say it's 1s2, 2s2, 2p6. So there's 8 electrons in that outer energy level there. It's an octet. That's what makes it stable. We've talked about that. But really what makes it stable is the outer energy level is full of electrons. And then you have to start talking about the stability that goes with charges and so on. Okay, the highest main energy level, well, that's easy. It's going to be 2 for all of these. 2. Let's put that in. And we already did the number of valence electrons up here. So this has 1, 2, 3. And this should be sort of a review from ionic compounds when we talked about oxidation states. But the things that confuses people is we always just said, well, fluorine is a -1. Because that means fluorine is going to gain an electron. That's why it's -1. Okay, now we're going to get into these dot diagrams, which actually are very simple. You draw out the name of the element. We have lithium, and there's 2 electrons that can go on each side of this. Really, this is just showing us the valence electrons. It's not showing us all of those inner subshells and orbitals. So we have 1 valence electron. That's it. See how easy that is? All right, beryllium. We have 2 valence electrons. Boron, 1, 2, 3. Carbon, 1, 2, 3, 4. And you don't really have to put these in any specific place around here. I'm just going to the right. Nitrogen, 1, 2, 3, 4, 5. Oxygen, 1, 2, 3, 4, 5, 6. Fluorine, 1, 2, 3, 4, 5, 6, 7. And of course neon has the full octet. Now why do people draw these? Well, really it'll make it easier for us to show how these bond together in molecular compounds, which is what we're going to learn. But also visually I can say, well, this has a full octet. It's going to be non-reactive. It'll be stable. Oh wow, fluorine just needs 1 electron. Lithium wants to get rid of 1. So that's why we draw these. Ionic symbol. So that's just going to be lithium. And remember, this is a metal. Think about it. Is it going to be easier for lithium to get rid of 1 electron? Or will it be easier for lithium to gain 7 electrons? To be just like neon. If I get rid of 1 electron, I'll be just like helium. Well, of course it'll be easier to get rid of 1 electron than gain 7. So lithium's going to get rid of this 1 electron. The electrons are negative, which means lithium will have more protons and make it a +1 charge. So that's where that positive charge comes from when we talk about group 1, when we talked about ionic compounds. It's losing 1 electron. Okay, beryllium, yet again it's easier to lose 2 electrons. It'll be a 2+. Both of those are leaving. If I go over to boron, boron says, yeah, man, all these electrons are leaving right now. They're leaving me. So 3 plus. Now carbon is a little weird. We really didn't talk about carbon, or really didn't talk about this group at all much when we did ionic compounds, because carbon can, think about it, it can lose 4, but it can gain 4. And also, it's not a metal. So, like, what is carbon? And that's why we sort of ignored it when we were doing this last unit. But right now, I'm going to put carbon, which would be like a 4 plus or a 4 minus. Okay, now think about this. These are going to gain electrons. This is going to be much easier for nitrogen to gain 3 electrons. Okay, and all those electrons are negative charges. So that's just going to be 3 minus. Oxygen, 2 minus. Fluorine, 1 minus. And neon's just here. It's not going to gain or lose. Okay, ionic electron configuration. This is a little bit weirder. Alright, let's think about this. If this loses 1 electron, this entire energy level is going away. So really, lithium is just going to be 1s2. Beryllium is going to lose 2. Oh, wait a minute. We're starting to see a trend here. That'll be 1s2. Boron's going to lose 3 and be just like helium, 1s2. And well, carbon could do all sorts of things. So it could be 1s2, or it could be like neon, basically. So it could be like 1s2, 2s2, 2p6, which is sort of strange. Okay, nitrogen. Well, yet again, nitrogen's going to gain, so it'll be just like neon. So it's going to be the same as that, essentially. I'm not going to write it all out. Same thing here. It'll be the same. Same thing. So now we're starting to see the whole point of these valence electrons, which are lost and gained. Now, Bohr models tend to have little circles. There's the first energy level. Here's the second energy level. And all of these only have 2 energy levels. So the first energy level can only hold 2 electrons. And the second energy level can only hold 8. So I'm going to write out the Bohr model based on the original lithium, which is going to have 1, 2, then it'll have 1 more electron. Beryllium will have 1, 2, then it'll have 2 electrons in that outer second energy level. 1, 2, that's the first energy level. Now the second energy level, there's 3. 2 in the S subshell and 1 in the P subshell. So here's 3. 1, 2, and then this will have 4. Yet again, normally people are like 1, 2, 3, 4. Okay, this will have 2. Then it'll have 5. Kind of in a Bob Ross moment here, just sort of bubbling these in, being very relaxed. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6, 7. Now keep in mind the first 3 periods are much easier. As you go down the table, it gets way more complicated. And this is also why, in my opinion, Bohr models really aren't very useful after about the 3rd or 4th period, because it just gets way too, I guess, cluttered, basically. Okay, so if you think about it, these are sort of like abbreviated Bohr diagrams, except they only show this outer shell. They don't show the outer, they only show the outer energy level. They don't show any of these electrons in the inner energy levels, which when we're talking about bonding, and now we're going to talk about covalent bonding, that's really all we need to worry about. So that's why we're not really doing Bohr models anymore. We're looking at just the valence electrons. So that's a real brief introduction to these electron dot models. Next video, we're going to go a little bit more in depth, and then probably make a few more videos just on all the different aspects of writing out these dot diagrams and then Lewis structures. Alright, I hope that helped. And if you have any questions, as usual, let me know.